Hey friends, Dr. Borole is here. Today we are going to learn the pressure sensors and pressure measurement techniques. The pressure is measured in various units like Pascal, Newton per meter square, PSI, kg per centimeter square, mm of Hg or mm of water column. The negative pressure is also measured in torr. Normally torr is the unit which measures the pressure below atmospheric pressure, that is vacuum. Pressure P is defined as force per unit area, that is P is equal to F by A. So if area of cross section is larger, the pressure will be smaller. So this principle is used for measurement of pressure. Force is converted to pressure by applying it to a specific area, and force by area is giving you the pressure. Pressure of a fluid is basically a compressive force that is exerted per unit area. The various pressure transducer used for measurement of pressure are listed here. The two basic types are used. Gravitational pressure sensors. These measures the pressure against gravity. Mostly the manometer comes in this range. Various types of manometers are there. Water manometers, mercury manometers are very common. The fluid selected will be depending on the particular area of the application. But mercury manometers are very common and they measure the pressure directly in terms of mm of Hg. The elastic type of pressure sensors, those are mostly using the elastic diaphragms or elastic capsules or bellows or Warden tubes. We will shortly see these mechanical devices and how they measures the pressure. Basically, diaphragms, the mechanical capsules, the bellows and Warden tubes, these are the mechanical transduction devices. The mechanical devices, diaphragm, capsules, bellows or Warden tubes. These are basically primary transduction devices. These devices basically transform the pressure into displacement, and displacement will be then converted to electrical signal by a secondary transducer. Many a time this can be done by using a strain gauges or capacitive type of transducers. The pressure to displacement is done by these mechanical devices, and the displacement can be measured by using strain gauges very commonly. The strain gauges converts this mechanical strain to proportional resistance. Various types of mechanical elements, the primary sensors used in pressure sensings are listed below. The strain gauges, the load cells, the diaphragms, the capsules, bellows and Bourdon tubes are quite common. Let us see what is strain gauge. The principle of operation of the strain gauge is when a strain is applied to a strain gauge, it changes the length. Strain gauge is basically a metallic wire. When the strain is applied to the metallic wire, it elongates. When it elongates, the resistance of the wire will be changed. The change in resistance is proportional to the elongation. And This change in resistance is a passive quantity that will be further converted to electrical signal by using the Wheatstone Bridge type of circuits. And therefore, strain gauges converts the strain or mechanical displacement which creates the strain into proportional electrical signal. So therefore, we can conclude that change in resistance is proportional to change in length, that is shown here. Delta R is proportional to delta L. Let us define some factor. It's called gauge factor of the strain gauge. It is also called as sensitivity of the strain gauge, and it is defined as gauge factor GF is equal to delta R by R upon delta L by L, where R is the resistance of the gauge and L is the length of the gauge. Delta L is a change in length of the gauge due to applied strain, and delta R is a corresponding change in resistance. Now, once the mechanical displacement or strain will be converted to resistance, then we can convert this change in resistance to the proportional voltage, and that can be done by using Wheatstone bridge. The circuit shown here comprises of four resistances. Out of that, one arm constituted by a strain gauge. So R1, R2, R3 are the general resistances, and R4 is a strain gauge, and it is connected in a Wheatstone bridge form. VDC is a biasing DC power source, and the detected output from the Wheatstone bridge that is connected to the amplifier. Amplifier just provides the additional gain and high input impedance to avoid the loading of sensing bridge. The output voltage of the amplifier is then proportional to change in resistance. We will shortly see the analysis and calculate the output voltage. Here in the first figure, only single strain gauge is shown, and that replaces arm 4. Whereas for higher sensitivity, all four arms can be replaced by four strain gauges, and these strain gauges are connected to the load cell where strain is measured in such a way that they will provide highest sensitivity, that is, they will provide highest change in resistance. We shortly see this. Various types of strain gauges, they are classified as shown in the figure. They can be wire strain gauges or they can be semiconductor strain gauges. The name itself indicates that the wire strain gauges are made up with the metallic wires, whereas semiconductor strain gauges are made up of semiconductor material. The wire strain gauges are classified as unbounded or bounded or foil type of strain gauges. Typical construction of a foil strain gauge is shown in the figure. See here there is a base former, that is a flexible material on which very thin sheet of metal wire is printed either by screen printing or other sputtering methods. So here this structure, metallic structure is printed, and this wire, zigzag wire is shown here. Here the gauge length is shown in the figure, and the direction of applied strain is also shown. So whenever this gauge is applied with the external strain or force, which will pull these wires. When these wires are getting pulled, its length will be increased. When length is increased, obviously the diameter of the wire will be reduced. And as we know, if the diameter of the metallic wire is reduced, the resistance of the wire will increase. Therefore, elongation of the strain gauge wire will increases the resistance by say amount delta R, which is proportional to applied strain. So, if we apply the strain in the particular direction, then only wire get elongated. If you apply the strain in horizontal direction here, in x-axis direction, then no wire is getting elongated and therefore there is no change in resistance. Whereas if we apply the strain in y-axis direction as shown in the diagram, the wires are getting stretched and therefore resistance will be changed. The similar figure is repeated here, which is in color form. Since these wires are very thin and printed on a flexible base, they are in the form of a foil and therefore it is called as foil strain gauge. Operation of the strain gauge, I just explained. Same thing is shown in this figure. In this figure, let us see. The strain gauge is shown here horizontal. So in x direction, if we apply the tension to this strain gauge, the wires are getting elongated and therefore there is a change in resistance. Whereas in vertical direction, the gauge is insensitive to strain applied externally. Whereas the external strain or force applied, that is called tension, or it can be in the form of compression. When it is a tensive force, the wire length will increase and the resistance is increased. If it is compressive force, that causes the wire length reduced and therefore the resistance will decrease. This is shown here how this strain gauge is mounted. See, it consists of a rigid support and there is a mechanical beam like a structure, and the strain gauges are mounted on the surface of this beam. Say 1 and 3 and 2 and 4. There are 4 strain gauges mounted. You can have single strain gauge or 2 strain gauges or you can have 4 strain gauges. So whenever force is applied to this cantilever beam, which is flexible enough, due to this pressure, there is a stress developed in these strain gauges. The upper strain gauges 1 and 3 gauge the tensile stress, whereas the strain gauges 2 and 4 gauge the compressive stress. So resistance of 1 and 3 is proportionately increased with the pressure and the resistance of 2 and 4 strain gauge will be proportionately decreased with the applied pressure. Here same is shown in the figure below. The normal strain gauge, foil strain gauge is shown. Terminal connections are also shown and there is no deformation in the first figure A. When the foil is slightly bent, there is a tension created in these wires of the foil strain gauge and the resistance changes. Here in figure C, there is a compressive type of strain developed in the strain gauge due to bending of the strain gauge to the inner side. The same happens here on the cantilever beam. So additional figures are shown for better understanding. So now we get from the strain gauge, the pressure is converted to proportional change in resistance. If these strain gauges are connected in the bridge form in the appropriate branch, then the bridge output is proportional to the change in resistance. If four strain gauges are used and they are connected appropriately in the cross arms, then the sensitivity of the bridge will be increased four times compared to single arm strain gauge connection. And that's why to have larger sensitivity of the measurement, normally four strain gauges are used in four arms of the Wheatstone bridge. Various advantages and disadvantages of semiconductor strain gauges. Advantages are in semiconductor strain gauges have larger delta R compared to metal alloy gauges. Means they are having higher gauge factor. They are chemically inert or the semiconductor gauge can be manufactured with the chemical inertness. They are small in size compared to wire strain gauges or metallic strain gauges. Various limitations of semiconductor strain gauges are they are having poor linearity. They are most expensive also, and they are sensitive to temperature because we know semiconductor devices are having temperature dependent performance. And therefore, semiconductor strain gauges are used normally where the temperature is not varying widely. They are having higher sensitivity. Application of the strain gauges. Strain gauges are normally employed for measurement of pressure, measurement of weight, and measurement of level. We have seen very common application of weight measurement and electronic weighing system at various places and at various shops. And at large scale, we will look at the truckload measurement by using weighing bridges. Typical application of the strain gauge is electronic weighing machine. A block diagram of weighing machine is shown here. It consists of a load cell. Load cell is basically a mechanical structure, and on this load cell the strain gauges are stick or pasted. When the object is placed on the load cell, it exerts the pressure on the load cell, which causes the deformation of the mechanical structure inside, and that creates the compressive strain. Whereas if four strain gauges are used, set of strain gauges gets elongation and set of strain gauges get the compression, and therefore there is change of resistance exist between the various strain gauges. The output of the load cell is basically a change in resistance. Change in resistance can be converted to a electrical signal by using Wheatstone bridge. Majority of the time, the load cell unit itself includes the Wheatstone bridge. So therefore, the practical load cell available in the market, they can directly provide the output in terms of voltage, which is proportional to the weight of the object. Since this signal is a smaller signal or in millivolt signal, it needs to be amplified by the amplifier, and therefore amplifier block is used. It can be basically a integrated circuit amplifier. Amplifier can be connected directly to analog instrument, or they can be connected to a digital system, and most of the time nowadays we will see the digital indicator. For that purpose, we will convert the analog output from the amplifier to digital signal, and that can be done by A to D converter. A to D converter will be operated under the control of a microprocessor nowadays, and this microprocessor get the samples of the analog signal converted to digital signal, and those digital readings are stored in the memory of a microprocessor based system. Microprocessor can also provide the linearization if required for the sensor, and then the digital data corresponds to the weight that will be displayed via display driver on the display unit. So if the weight changes, there is change in the electrical output of the load cell that will be converted to the corresponding change in the digital data, and then this digital data will be reflected on digital display. And this application we have seen in our laboratories also and at various grocer shop nowadays. Same block diagram is applicable for larger weighing machines. They can measure the weight in tons. Just for additional information, I will show you here the load cell also. See, load cell look inside like this, shown in the figure. It consists of a mechanical column and to which the strain gauges are applied. Here the two strain gauges are shown, A and B, and it is attached to the rectangular steel bar. The pressure is applied to this steel bar from the top end. When the pressure is applied, there is a deformation of this steel bar that is very small in fraction of micron. Due to this deformation, there will be the strain develop in the strain gauges, and therefore there is a change in resistance. This change in resistance is very small in the range of few milliohm, and this few milliohm change in resistance can be converted to electrical voltage by Wheatstone bridge. This another figure also show the internal structure of a practical load cell. You will see here there is a load cell column to which the pressure is applied, and to this elastic load cell basically a structure of a metal to which the strain gauges are pasted, and these strain gauges are connected to the wire to the external terminals. The cross section view is shown here. From outside, this can look physically like this. That load cell in this first figure, here this horizontal bar is basically a load cell, and the strain gauges are attached to this horizontal bar, one from top side and another from bottom side. This is cantilever type of strain gauge, whereas in these first two figures the column type of strain gauges are shown. Here another shape of strain gauge is shown. Here the pressure is applied from the top side and there will be the development of strain. So the strain gauges can be pasted here. In these slots, the strain gauges are pasted. One is here and another is here, and these strain gauges terminals are taken out, and these wires can be used further for connection in the bridge form. Another structure shown here. So whenever the pressure is applied here, there is a deformation of this slot. So in this slot, the strain gauges are pasted. One is from the bottom side of this top edge and another is shown here on this portion. So therefore, when strain is applied, there is a change in resistance of the strain gauge, and these strain gauges wires are connected and available for external connection via wires. Another type of load cell is shown that is totally hermetically sealed inside. This is that column. This strain gauge shown here The internal cross-sectional view is shown in this figure 2 or figure 1. Outside, it looks like this. So when pressure is applied, the strain gauges are actually inside this assembly. The output available from the strain gauge that can be connected to the electrical system for display purpose. Various types of practical load cells are shown in this figure. That's all about the strain gauges, friend.